Hey guys, I'm Pat Kelly. Okay, got a lot to do in this one, so I hope you're sitting down. They give us this function f of x. We are supposed to find its inverse, graph both f and f inverse, the same set of axes, describe the relationship between those graphs, and then wrap it all up by giving the domain and range of each of those two functions. Okay, so let's take it slowly. Where they want us to begin is to find the inverse. All right, so the work you're going to do for that starts with the f of x that they give you, but the first thing I do is I rewrite the f of x as just y. You know that they're interchangeable. And keep the other side, of course, x to the fifth minus 2. And then the next step's a little bit goofy. In terms of doing proper procedural mathematics, the next step's really not legitimate, which is why I put like a little dashed line in my work, because if somebody comes in and sits down later on and sees this first step and then my next step, they might ask, how did you get there? Because there's no algebraic explanation. Because what you're going to do in this next step is swap the roles of x and y. So this y becomes x, and this x becomes y. And that's why I was making such a big to-do about this, is how do you go from this step to that step? There's no mathematical reason other than we're working to find that inverse. And what we do with this new equation now is solve it for y. And if you can do that, that's your inverse. So let's solve this guy for y by first adding 2 to each side. And then just one more algebraic step, right? Take the fifth root of each side. I'll switch the sides too, just because we like our y's to be on the left. If I take the fifth root of that left-hand side, there's just x plus 2. There is not a plus or minus. I know there's a radical involved, but that's only square roots, fourth roots, even-powered roots. So that's my y equals. I was able to do it, no problems, algebraically, which means that's my inverse. So I have an answer, and leave a little bit of space for some more work that we have to do yet. But I have an answer for f inverse. It equals that fifth root of x plus 2. Okay? All right, part A, done. Part B, graph both of these. Okay, so now to graph each of these, let's look at f of x. And I need to go off to the side to do a little bit of scratch work. Okay? And all I really want to do is show you, if I'm going to graph this, consider what the parent function looks like. Okay, we've done some work with parent functions before. Okay, the parent function here, if this is x to the fifth minus 2, the parent function would just be x to the fifth. I'm just kind of scratching that minus 2. The reason I want to do that off to the side is because you do want to know what the graph of this guy looks like then. Just a quick rough sketch. And any x to an odd power looks like that x cubed guy, that little S-shaped snake type thing there. Okay? So all I'm doing is, now back to my function, is subtracting 2 from that. Let's do the official graph then. I'm trying to do that S shape, but shifted down 2, right? So I'm probably looking at something like this. Down to a -2 on the y-axis, and then continue. Okay? Not bad, I think. Now let's do f inverse. Same scratch work again in terms of just identifying what its parent would look like. And this time, the parent, you think of disregarding the extra stuff, which is just the plus 2 this time. My parent would just be that fifth root of x. Fifth root of x. Which again, I'm doing the scratch work just because you want to have a feel for what the graph of that looks like. And again, comparable to like the cube root here. So your odd indexed radicals really all look the same. Comes down to like stretching factors. So I'm looking at that as my parent. So for mine, I have a plus 2 on the inside, which is a horizontal shift 2 to the left. So when I go to do my graph over here, I'm going to try to draw something that looks like that parent, but shift it over to. So let's say it looks something like this. See how I did. You might see why I did math for my life choice, not art. Okay, I think we're good. Relationship. The relationship between the two graphs that we just did. I'm going to grab another color here and try to draw a nice 45-degree slant. Okay, approximately. And I'll try to do this in a dashed line here. Because what you're looking at in terms of the relationship between the two functions f and f inverse with the graph is that that dotted line is like a mirror. I think it looks pretty good. This pink colored curve looks like it's orange if you're reflecting through that y equals x line. I should have told you that's what I was drawing at the 45-degree slant. Okay, so those two graphs, this should always happen for all these problems. The function and its inverse should look like mirrors of each other if your mirror is that y equals x line. Okay? All right, let's wrap it up with the domains and ranges. And I'm glad we have our graphs here for the domain and ranges, because that's what I'm going to look at. The f of x, that was this pinkish one for me. The domain here, if I have my graph, that's the x values as far left as I can go and as far right as I can go, and these graphs do continue to bend over. Okay, so this is actually the minus infinity to infinity situation. You know what? That should also make sense to you for domain, because there's no division by zero and no square roots of negative numbers, so all values are possible. Okay, now your range, let me switch. Your range for f of x, again, I'm glad we have the graph. Now you're looking at how far up the y values go and how far down the y values go. That's also negative infinity to infinity, right? Okay, your f inverse function, its domain. Now I'm looking at the orange graph, domain, x values forever to the left, forever to the right. So my domain is that, negative infinity to infinity. And my range, if I look at the orange graph, it does actually go up, up, up very gradually, and it goes down, down, down very gradually. It's a negative infinity to infinity situation again. Okay. Now, mine worked out nicely, but watch this, and I color-coded these for you on purpose. The range of your one function is always going to end up being your domain of the other. All right? And likewise, the domain of the first is going to be the range of the second. Look for that in your own problems. Okay, I need to take a break after that. But you keep at it. Do your own work now.